So till now we have done the expectation problems, no? From now variance problems will do. Here this example problem, if you see 6.10, let the random variable capital X have the distribution. They gave some distribution. They given in different form, not in tabular form. Probability of x equal to 0, probability of x equal to 2, both probabilities are equal to p, small p. Probability of x equal to 1 is equal to 1 minus 2p. Okay, the probability of x equal to 1 probability value is given, probability of x equal to 0, probability of x equal to 2 probability value is given, and this probability p is there, na? That range is from 0 to 1 by 2. Probability of success actually lies in between 0 to 1, but according to this problem they have given that this p lies in between 0 to 1 by 2, means p will take value even 0, 0.1, in between values of 1 by 2 and also 1 by 2. That means p is taking between values, even the extreme values of this range. That is the meaning. Okay, next they are asking us for what p is the variance of capital X a maximum. So p is taking value 0 to 1 by 2, no? So what p value makes variance of x maximum? So now that depends on the formula of variance of x. So if variance of x is just p, the highest point will give us high variance. If it is 1 minus p, that depends on the p value. If it is 2 times p or 4 times p, as p increases, variance increases, correct? So we'll decide once we'll get variance of x value in terms of p. Solution: here the random variable capital X takes the values 0, 1, 2. All three values it is taking 0, 1 and 2 with respect to the probabilities. With respect to probabilities, 1 minus 2p and p comma p means probability of x equal to 1 is 1 minus 2p. So here first they written p here p 1 minus 2p and p respectively, na? When x equal to 0 it is p, when x equal to 1 it is 1 minus 2p, when x equal to 2 it is just small p. P lies in between this range. Thus expectation of x, see, we are using to find variance of x the expectation formula. So what expectation formulas we require to find variance of x? Expectation of x square minus expectation of x we want. So this expectation of x is mean value, and expectation of x square we want. So expectation of x square here, expectation of x. What is the formula? Summation x takes values 0 to 2, small x into p of x. So p of x is when x equal to 0 just p, when x equal to 1 it will change 1 minus 2p, when x equal to 2 it is just again p. So like that the probability value will change, probability mass function. Summation x p of x, that is the formula of expectation of x. What is expectation of x square? Summation x takes value 0 to 2, x square probability of x. Here x square will be there, here just x. So first here take 0, and probability of x equal to 0 is p. So p 0 into p plus next 1 you take. When x equal to 1, then 1 minus 2p. So 1 into 1 minus 2p. The last one, when it is 2, the probability is p. Done. This part is equal to 1. Why it is equal to 1? Here p, here 1 minus 2p, here plus 2p. Correct? So plus 2p, here it is 0, ma? Here it plus 1 into this part, that means 1 minus 2p plus 2p. So 2p get cancelled, you will be having only 1. So mean of this problem is 1. Expectation of x square is 0 square, which is 0, plus p, probability of x equal to 1 is p, plus x square, which is 1 square, into probability of x equal to 1 is 1 minus 2p plus x, the other value, x2 square into p. So here it is 0, the first term. Here it is 1 minus 2p. Here it is 4p. 1 minus 2p plus 4p, which is 1 plus 2p, correct? Variance of x is equal to this 1 plus 2p minus 1 square. 1 get cancelled, will be having only 2p as our answer. So variance of x is equal to 2p and p lies in between these two. So when p increases, this function also increases, monotonically increasing function. So obviously for 0 less than or equal to p less than or equal to half, variance of x is maximum when p equal to half, means at extreme point this variance of high extreme point, variance of x will be maximum, and variance of x maximum is equal to 2 into 1 by 2, which is equal to 1. So variance is equal to 1 at p is equal to half. If you take the middle values, it won't be equal to 1, it will be less than 1. So variance of x is maximum at p is equal to half. Got it? That's the solution for this problem. Now let us take the next example problem, random walk problem. Random walk means a person is walking, even he don't know in which direction he is going to take. He'll take whatever direction randomly, and that's why it is called a random walk problem. Random walk means even the person who is walking, even he don't know which direction he is going to walk. That is what random walk problem. Starting from the origin, he is starting from his standing position until unit steps are taken. So unit steps are taken to the right with probability p. So if he is standing here, if a unit step is taken to the right, with the probability p, to the left same unit step with the probability 1 minus p or q. Assuming independent movements, means if he is moving one movement, that movement does not decides the next step. So find the mean and variance of the distance moved from the origin after n steps. So he did some n steps, he moved to n steps, and we want to find mean and variance for the distance moved from the origin after n steps. Solution: let us associate a variable xi with the ith step defined as follows. So xi is the variable. Xi will take +1, xi will take -1. +1 whenever he go towards right, -1 when he step towards the left. That's why we are taking x values 2, +1 -1. Then s is equal to, capital S is equal to sum of all independent steps. x1 is first step, x2 is second step, n steps, no? All steps, sum is s, that is what sample spaces is equal to summation xi, represents the random distance moved from the origin to after n steps. Expectation of xi, variance of xi. How to find expectation of xi? This is mean, this is variance. If you want to find variance, you need mean as well as expectation of x square also. So first expectation of xi is equal to summation x is equal to -1 to +1, only two values, -1 +1. When x equal to +1, when x equal to -1. So when x equal to +1 and its probability is p, that is given. When x equal to -1, its probability is q. Anything, you can write first this one as first and this one as second, or this one as first or this, that is up to us, which is equal to p minus q. The value is here p minus q, mean value p minus q, and expectation of x square is same, 1 square plus p minus 1 square plus into q. So now it is p plus q. Here p minus q, no? Here when square comes, the minus becomes plus, so p plus q. It is equal to 1, that we know. Total probability always equal to 1. Correct? Yeah. So next, variance of xi now. Take expectation of x square minus this part. So expectation of x square is p plus q, no? P plus q whole square minus this one is p minus q whole square, which is equal to 4pq. You will get, if you expand a plus b whole square, a minus b whole square, and you will get 4pq. Next, hence expectation of Sn. What is Sn? This is S. S or Sn is equal to summation. When we give some expectation of sum of this part, expectation of this, that is nothing but summation expectation of xi. So summation expectation of xi, which is equal to n into p minus q. Correct? Mean value is given, expectation of xi value is p minus q. So we are substituting expectation of xi p minus q here, so that summation p minus q, here summation actually, I takes values 1 to n. When we write p minus q, which is constant with respect to summation, so take it out. Take p minus q outside and you will be having only summation 1. So that 1 is added n times. When it is added 1 times, you will get n as your value. That summational value is n p minus t. And variance of Sn, we are finding here expect mean of sample space. Variance of sample space is equal to summation Vxi that we know, which is equal to 4 times npq. This is 4 times npq. Okay, here any doubts? This one. Next, therefore, or since movements of steps are independent, they are independent here. Next, example 6.12. Let x be a random variable with the mean mu, variance sigma square. Show that expectation of x minus b square as a function of b is minimized when b is equal to mu. Solution: expectation of x minus b square is equal to expectation of x minus means in between we are subtracting mu, adding mu, so that we'll get x minus b only. So x minus mu plus mu minus b. If you take like this one get cancelled, x minus b only will get whole square is equal to expectation of x minus b a plus b whole square. So 2ab, which is equal to, and give the expectation after expanding, give the expectation, and then which is equal to, this is nothing but expectation of x minus expectation of x whole square, which is variance of x. This is mu minus b square, this is plus 2 mu minus b, and expectation of x minus mu. Here expectation of x minus mu value is equal to 0. We already have proved that expectation of x minus mu is expectation of x. Expectation of x minus expectation of x is always equal to 0. So when this part is equal to 0 and this entire covariance part is 0, and you will be having this one and this one. Okay, so expectation of x minus b square is equal to variance of x plus some additional part is there. Some additional part, you understand, some additional part. So we can simply say that this expectation of x minus b square is greater than or equal to variance of x. Only one term is variance of x, and some additional term is there for the expectation of x minus b square. That means expectation of x minus b square is a bigger value compared to variance of x. So finally we can write expectation of x minus b square greater than or equal to variance of x, since mu minus b whole square being the square of a real quantity is always non-negative. It should be a non-negative. If you get negative value or positive value, it is always negative value, positive value, because square is there. The sign of equality holds in the star if and only if that mu minus b whole square becomes 0. When this is becoming 0, then only this one and this one here, this is star equation. Equality will happens whenever this part is equal to 0. That means mu equal to b. Hence expectation of x minus b square is minimized. This value will be taking a minimum value. Actually it is maximum than variance of x, and it will be minimum means it is equal to variance of x only when mu equal to b, and its minimum value is expectation of x minus mu whole square is equal to sigma x square. When we write this equality condition here, when this equality condition comes, when it is equal to 0, and expectation of x minus b square is equal to sigma suffix x square. You can also denote this notation as like that. Next, that is what we proved. Example 6.13. Now we have one more example. I want you people go through it. Actually here we are going to take a Bernoulli distribution. This example 6.13 is a Bernoulli distribution. So here you are already aware of Bernoulli distribution, binomial distribution, Poisson distribution, and normal distribution, na? So I'll explain you. You people needs to try to understand this. Otherwise you will understand this once we'll go with the distribution. Next unit is complete distributions. Okay, in a sequence of Bernoulli trials means the random variable x will take only 0 and 1, two values. That means x equal to 0 means that trial not happened. X equal to 1 means trial happened. Means take it coin tossing. If you toss a coin one time, it follows Bernoulli distribution. When you toss coin for 5 times, and this addition of this whole experiment follows binomial distribution. You understand? Only one time toss follows Bernoulli distribution. Toss like 5 times. If you toss, that addition of all the tosses follows binomial distribution. That is the difference between or interlink between Bernoulli distribution and binomial distribution. And in a sequence of Bernoulli trials, let x be a length of the run of either successes or failures. Starting with the first trial, find expectation of x and variance of x. Solution: let p denote the probability of success, and then q is equal to 1 minus p is the probability of failure. That is our assumption. P is represents the probability of success, q represents probability of failure. Q is equal to 1 minus p. X is equal to 1 means that we can have any of the probabilities SF and Fs with respect to the probabilities PQ and QP. What is SF and Fs? SF means success failure, failure success. That is nothing but PQ and QP. So probability of x equal to 1 is equal to probability of success a failure plus probability of failure success, which is equal to probability of PQ. This value is PQ and this value is QP, which is equal to 2PQ. Probability of x equal to 1 is that, and probability of x equal to 2 is probability of success failure plus probability of failure success. You understand? Run, we are here, x denotes the run, RUN. Run means either success should be having two successive values should first, for example, first one is yes, the successive value should be s only when x equal to 2. When x equal to 1, no problem, yes, f or fs. Okay, only one time it should be repeating. Here 2 means 2 times either s should repeat or f should be repeating, and we'll be having 2 cases, and that cases probabilities are, in this case yes, which is success, 2 times p square, and failure q. Here success is p only one time, q which is q square. So p square q square p. In general, probability of x equal to r. So 1 we know how to write, 2 we know how to write. What if x equal to r? X equal to r means probability of yes and so on. Yes, this is r times p. That means rp you will get, or p power r. This p power, it is multiplication, p power r you will get. F means q. Here q power r p. So p power r q power r p. That is what the general thing from the problem, given problem they have given like that. That run represents the probability p, s represents probability p, f represents probability q. In general, that is over. Therefore, expectation of x is equal to summation r into probability of x equal to r. We are finding mean here. Summation r is the variable here. R is equal to 1 to infinity. R into probability of x equal to r. We know probability of x equal to r. This is the thing, which is equal to r into probability of x equal to r is this, which is equal to pq. Here this pq we are taking out. From here q we have, but p is not there. Even though p is taken out, here p is there, q is not there. So both pq taken means p power r minus 1 will be there, q power r minus 1 will be there. If you want to take pq outside, you will see r into p power r minus 1 plus q power r minus 1. So summation r is equal to pq is taken out. So summation r is equal to 1 to infinity into r p power r minus 1 plus summation r is equal to 1 to infinity r into q power r minus 1. You understand how we taken PQ out from this and from this. If you want to take P, actually P is not there. So what you need to do is P divided by P, which is 1 only. So P by P, you taken PQ out and divided by P will be there. That P is nothing but P power R minus 1. Here also same, Q power R minus 1. Okay. Next, so PQ and expand this so that we will get this and which is equal to PQ, and this expansion is 1 minus P whole power minus 2. Series expansions, you need to know the formulas, plus this expansion is 1 minus Q whole power minus 2, and PQ, this expansion from this expansions after the cancelling, ones will get cancelled, na? PQ, this is 1, it is 1 and plus 1 minus P power minus 2 PQ, okay fine, Q power minus 2 P power minus 2. Actually we need to expand this like 1 minus A minus B whole square, A minus B whole square formula. If you expand this so that we can cancel it, or else you can write 1 minus P whole power minus 2 as 1 divided by 1 minus P whole square, plus this one as 1 divided by 1 minus Q whole square. If you expand also with that, you will get like this, Q power minus 2 plus P power minus 2, which is equal to the same PQ, and this can be written as 1 by Q square plus 1 by P square, which is equal to P by Q plus Q by P. When you multiply it, here Q get cancelled, so P by Q, here P get cancelled, so P by Q by P square, P by Q by P. So that is what expectation of x mean value, and variance of x is equal to expectation of x square minus expectation of x whole square, which is equal to expectation of x into x minus 1 plus expectation of x minus expectation of x whole square. And now here expectation of x into x minus 1 is there, na? How we got this? Actually from this we are writing this equation as expectation of x into x minus 1. If you expand it, x square minus x. So here we are writing expectation of x square as like this, expectation of x into x minus 1 plus expectation of x, and here some cancellation will happen, expectation of x minus expectation of x, so that we will get expectation of x square only. So this expectation of x square is writing like expectation of x into x minus 1 plus expectation of x, and the last part is same. Hope you understand this. You expand this, multiply it and then cancel it, so that you will get expectation of x square only. Now expectation of x into x minus 1 can be written like this, so which is nothing but finally we will get like this, 2 into p square by q square plus q square by p square if you expand this, and finally variance of x is equal to, and expectation of x into x minus 1 is there, na? That value we are writing first, and expectation of x value we know, p by q plus q by p. Why we are doing this? We are not finding expectation of x square, we just found expectation of x. We can also find expectation of x square, but it becomes quite difficult, so we are doing like this. Even for the previous problems you can do this also the same way. So here expectation of x into x minus 1 we have like this, and we are substituting that value here, and expectation of x value we are substituting here, and minus expectation of x whole square, that is this part whole square, which is equal to, so that we will get finally which is equal to this part is equal to p by q minus q by p whole square plus p by q plus q by p, finally the value of variance of x. That's it. So try to understand this derivation. If you get doubts you can ask me, I'll send you this notes. Next, one more example here, that is about covariance. Here this part is covariance part problems. One problem, two problems enough. that we'll do in next video. Okay.